In the ever-evolving landscape of digital security, cryptographic hardware stands as the bedrock of robust, efficient protection for modern platforms, ensuring that sensitive data and operations remain shielded from an array of threats while maintaining seamless performance. This slide introduces the core theme: why hardware-accelerated cryptography is not merely an enhancement but an indispensable foundation that underpins platform security in today's interconnected ecosystems. At its heart, cryptographic hardware integrates specialized circuits and processes designed to handle complex encryption algorithms at speeds unattainable by software alone, thereby preventing vulnerabilities that could arise from computational bottlenecks or exposure to runtime attacks. The visual design, with its deep navy background accented by subtle circuit-like patterns and a central chip icon, evokes the intricate, reliable architecture of silicon-based security, symbolizing the fusion of innovation and trust. The subtitle, Secure and High-Performance Security Foundations, emphasizes the dual pillars of invulnerability and velocity, highlighting how hardware offloads cryptographic tasks from general-purpose CPUs, freeing resources for critical applications like real-time data processing in cloud environments or mobile devices. Below the main title, the explanatory line, Why Hardware-Accelerated Cryptography Underpins Modern Platform Security, sets the stage for a deeper exploration, inviting viewers to consider real-world implications, such as how without this acceleration, systems could falter under the weight of high-throughput demands in 5G networks or IoT deployments. This foundational slide serves as a gateway, priming the audience for the technical depth ahead, underscoring that in an era where cyber threats evolve hourly, hardware's role is pivotal in achieving scalable, future-proof security without compromising usability or efficiency. Delving into the imperatives of cryptographic hardware, this slide elucidates the multifaceted reasons why hardware support is paramount, framed through three interconnected domains: fundamental platform security, overcoming performance gaps, and enhanced key protection, each illustrated with targeted icons and concise yet impactful bullet points against a cohesive blue-toned layout that reinforces themes of reliability and defense. Beginning with fundamental platform security, modern digital ecosystems, from enterprise servers to consumer wearables, hinge on unyielding cryptography to safeguard core mechanisms, rendering them perilously fragile without hardware reinforcement. Trusted boot emerges as a cornerstone, meticulously verifying system integrity prior to operating system initialization to thwart boot-time malware injections, while remote attestation empowers devices to cryptographically attest their authenticity to distant servers without divulging proprietary details, fostering secure remote management in zero-trust architectures. Complementing this, secure storage fortifies sensitive data at rest through tamper-proof encryption, ensuring that even if physical access is gained, reconstruction remains computationally infeasible. Transitioning to overcoming performance gaps, the slide starkly contrasts software-only encryption's limitations, capped at a mere 29 megabytes per second for AES 256 implementations, with the blistering 100+ megabyte per second demands of contemporary network speeds, illustrating how this disparity engenders severe bottlenecks in data-intensive scenarios. For instance, video streaming workloads demand voracious post-decryption processing, such as transcoding and rendering, which exhausts CPU headroom and leaves scant cycles for concurrent encryption, potentially degrading user experience in bandwidth-hungry applications like 4K streaming or virtual reality feeds. Hardware acceleration bridges this chasm by parallelizing operations, sustaining fluidity across high-velocity data pipelines. Finally, enhanced key protection addresses the perils of embedding cryptographic keys within general-purpose system memory, RAM. Where they lurk as low-hanging fruit for exploits, hardware isolation erects formidable barriers, with memory protection sequestering keys beyond OS reach to evade volatile memory dumps, attack mitigation deploying layered defenses against runtime exploits like buffer overflows or rowhammer attacks, and secure registers providing tamper-evident vaults, dedicated silicon enclaves that cradle secrets impervious to software introspection. Collectively, these elements paint a compelling narrative. Hardware support is the linchpin transforming cryptography from a theoretical safeguard into a practical, performant reality, mitigating risks that software alone cannot conquer and ensuring isolation that preserves integrity amid pervasive threats. This slide crystallizes the dual essence of cryptographic hardware through its two core pillars: performance and security, presented in a balanced, side-by-side layout with rocket and shield icons respectively, against a dynamic navy backdrop that underscores acceleration and fortification, illustrating how these benefits synergize to elevate system resilience without sacrificing speed. On the left, the performance pillar dissects throughput and efficiency, commencing with CPU offloading, where intensive symmetric operations like AES encryption and SHA hashing are delegated to dedicated circuits, liberating the primary CPU for higher-level application logic and averting resource contention in multitasking environments. This is amplified by specialized instructions, leveraging hardware-optimized instruction sets such as Intel's AES-NI or ARMv8 crypto extensions to expedite encryption rounds and key expansion processes, thereby preserving software compatibility while delivering exponential throughput gains for standardized algorithms. Culminating in energy efficiency, the design highlights superior performance per watt metrics over general-purpose CPU cycles, a vital advantage for power-constrained domains like mobile devices and IoT sensors, where prolonged battery life and thermal management are non-negotiable for widespread adoption. Shifting to the right, the security pillar emphasizes isolation and integrity, anchored by secure key storage that generates and confines keys within impervious hardware boundaries, shielding them from OS or RAM exposure to elude scraping attacks like those exploiting memory forensics. Side-channel defense integrates proactive countermeasures against insidious threats such as differential power analysis, DPA, or timing discrepancies, embedding noise injection or masking techniques directly into silicon to obfuscate leakage vectors. Trusted execution further insulates cryptographic operations within segregated environments, guaranteeing operational integrity irrespective of main OS compromises, while the root of trust, bolstered by trusted execution environments, T, establishes an immutable foundation for verifiable system states. Together, these pillars not only accelerate cryptographic workflows but also fortify the attack surface, rendering hardware an indispensable ally in architecting systems that thrive under adversarial scrutiny, blending velocity with vigilance in a visually compelling dichotomy that resonates with engineers and decision-makers alike. Unveiling the diverse blueprints for cryptographic acceleration, this slide maps 4 architectural methodologies in a quadrant grid layout, each encapsulated in color-coded cards with illustrative icons, fostering a clear comparative vista on a sleek navy canvas that demystifies implementation choices from integrated simplicity to bespoke isolation. Top left, special CPU instructions embed cryptographic primitives directly into the process's execution pipeline, enabling seamless software compatibility while surging throughput for ubiquitous algorithms. Processes like those supporting Intel AES-NI, ARMv8 crypto extensions, or SIMD optimizations vectorize operations, transforming scalar bottlenecks into parallel prowess without necessitating peripheral hardware. Top right, integrated subsystems fuse dedicated cryptographic blocks into the system-on-chip, SoC, fabric, synergizing with secure enclaves such as ARM's Trust Zone to instantiate a silicon-rooted trust anchor for key management. Examples include Qualcomm's Secure Processing Unit, SPU, and ARM CRYPTOCELL712, which streamline deployment in compact, cost-optimized designs ideal for embedded systems. Bottom left, dedicated co-processors elevate isolation to paramount levels via autonomous physical chips or hyper-isolated cores, exclusively devoted to security tasks independent of the application processor. Luminaries like Apple's Secure Enclave Processor, SEP, Google's Titan M, and Intel's Converged Security and Management Engine, CSME, exemplify this approach, offering unparalleled compartmentalization for high-stakes environments where even transient exposures could cascade into breaches. Bottom right, partial acceleration adopts a pragmatic hybrid paradigm, confining hardware intervention to the most compute-intensive facets, such as big integer arithmetic or modular exponentiation in RSA, while software orchestrates ancillary functions, thereby curtailing silicon overhead and eradicating primary bottlenecks affordably. Capped with a subtle footer noting cryptographic hardware foundations and a timestamp, this slide empowers strategic selection by juxtaposing trade-offs in complexity, cost, and isolation, guiding developers toward architectures that align with workload exigencies and threat models in an era of escalating cryptographic demands. Anchoring cryptographic hardware in verifiable credibility, this slide dissects the FIPS 140-2 frameworks for escalating assurance levels through a progressive card array in grayscale to magenta gradients, each adorned with evocative icons like open locks for basic tiers and explosive safeguards for apex protections, set against a disciplined Navy expanse that conveys regulatory rigor and hierarchical progression. Level 1 establishes basic security with production-grade equipment and rigidly defined cryptographic algorithms, eschewing physical enclosures in favor of software crypto engines to certify foundational compliance without undue complexity. Level 2 introduces tamper-evident measures, holographic seals and coatings that indelibly reveal intrusions, coupled with role-based authentication, ensuring operator accountability in semi-secure deployments. Level 3 fortifies with tamper-resistant physical mechanisms and intrusion detection, mandating zeroization of critical security parameters, CSPs, upon enclosure breach to preempt data exfiltration in fortified settings. Level 4 crowns the spectrum as highest assurance, enveloping modules in comprehensive protection that autonomously detects and responds to unauthorized physical accesses, including environmental manipulations like voltage glitches or thermal faults exploited in fault injection attacks, culminating in key auto-destruction for mission-critical applications. Beneath, an expansive additional standards bar illuminates validation for hardware random number generators, RNGs, and primitives, invoking NIST SP800-90B for entropy source entropy assessment, ISO 18031 for overarching RNG conformance, and BSI-31 for statistical unpredictability, collectively ensuring outputs indistinguishable from true randomness. Footnoted with Cryptographic Hardware Foundations, and a date, this slide transcends mere certification enumeration, serving as a compass for compliance navigation, emphasizing how adherence not only substantiates security assertions but also satisfies stringent regulatory mandates, thereby bridging technical innovation with institutional trust in global deployments. Spotlighting the linchpin of cryptographic vitality, this slide dissects hardware random number generators, RNGs, via a tri-stage pipeline visualization flanked by critical dependency and implementation panels, rendered in a flowing yellow to green gradient on a Navy base that symbolizes entropy's chaotic genesis to ordered security, underscoring ARN's existential role in forestalling predictability-induced catastrophes. Encased in a bold red border, the critical dependency warns that protocols like ECDSA and DSA teeter on high-fidelity randomness for key generation, initialization vectors, IVs, and nonces. Predictable RNGs invite private key recovery, unraveling entire security fabrics in signatures or session establishments. The central pipeline delineates Stage 1, source, harnessing raw physical entropy from hardware phenomena like thermal noise or oscillator jitter for inherently unbiased yet noisy inputs. Stage 2, refinement, applying digital post-processing via deterministic random bit generators, DRBGs, and AES, SHA mixing to excise correlations and forge uniform distributions, culminating in output, cryptographically secure material primed for keys, IVs, and nonces. Rightward, real-world implementation spotlights Qualcomm's SPU, ingeniously exploiting electronic oscillator drift, subtle frequency variances, as an entropy fount, channeled into a hardware PRNG for prolific, high-caliber bit streams that permeate mobile silicon. Counterpoised, quality standards mandate rigorous statistical gauntlets to affirm indistinguishability from true randomness, citing NIST SP800-90B for entropy sourcing, ISO 18031 for holistic validation, and BSI-31 for probabilistic scrutiny. Timestamped footer reinforces Cryptographic Hardware Foundations, positioning this slide as an urgent clarion. RNGs are not ancillary but the unpredictable heartbeat of crypto, where hardware's physical idiosyncrasies transmute noise into the unbreakable randomness that fortifies digital fortresses against forensic unraveling. Synthesizing the discourse into actionable wisdom, this slide distills core principles and an implementation roadmap in a bifurcated layout, leftward verdant checkmark tenets against a Navy tableau, rightward a linear timeline of steps with a culminating integration exhortation, evoking culmination and forward momentum to encapsulate how cryptographic hardware forges enduring, adaptable security paradigms. Core principles commence with performance through hardware, wherein offloading symmetric crypto like AES and SHA-2 accelerators amplifies throughput for bandwidth-intensive workloads while curtailing power draw, enabling fluid operation in edge-to-cloud continua. Root of trust isolation affirms hardware-backed key vaults that safeguard secrets impervious to OS or application layer breaches, embodying compartmentalization as the ultimate bulwark. Entropy quality insists on premier hardware RNGs to obviate key predictability, the silent saboteur of robust protocols. Compliance assurance leverages benchmarks like FIPS 140-2 and NIST SP 800-90B to authenticate claims and fulfill regulatory imperatives, transforming adherence from obligation to competitive edge. The roadmap unfurls stepwise. Step 1, delineate requirements via throughput, MBPs, and latency benchmarks to align with operational imperatives. Step 2, Conduct threat modeling to catalog perils from physical tampering and side channels to software exploits, forging a bespoke risk taxonomy. Step 3. Curate selections, CPU instructions for agility, integrated SOC modules for seamlessness, or HSMs for impregnability. Step 4. Orchestrate validation encompassing FIPS certification and RNG statistical assays to empirically vindicate designs. Capped by the imperative, integrate security at the hardware level early in design. This slide transcends summation, emerging as a strategic manifesto that propels viewers from conceptual grasp to tactical execution, affirming hardware's role in sculpting scalable foundations where security and scalability coalesce, footnoted with Cryptographic Hardware Foundations, to seal the narrative arc.